Hello and welcome again to my Physics Online video lecture series. Today's video we're going to be starting off a new set of videos which pertain to what we sometimes refer to as modern physics. It's really like physics that happened in the last decade or so of the 19th century and on into the first third or maybe half of the 20th century. That we predominantly are looking at in modern physics. So this includes the development of the idea of the atom and our models of the atom. It includes quantum mechanics. It includes special and general relativity. It includes some nuclear physics, some spectra, the nature of light as a particle or as a wave. Some of these topics obviously we have encountered before. Here we are sort of re-encountering some of them, and some of them are actually new. And while this is kind of the first lecture in this series, I'm actually going to start off rather than giving like too much of an overview or anything like that, by introducing some units, some constants and a unit. And I've titled this one Two Constants and a Unit. You can be the judge as to whether it really is two constants or more, whether there are two new constants, whether there's only one new constant, and whether or not this unit is new to you as well. But the focus here is these two constants and a unit. They are basically things that we will be using throughout the modern physics, both for quantum mechanics and for all the atomic and molecular and so on. So let's get into that. There's not really anything in the recall part of this per se, but we could maybe start off with a recall if we want to go out of order from the title. In other words, if we want to introduce the unit first and then the two constants, somehow the title two units and a constant just had a better sound to it than a unit and two constants did. So let's begin by recalling, and we'll start off with the unit part of it. So recall. In electrostatics, the work done on a particle, or the change in potential energy on a particle, is given by the particle's charge, Q, times the potential through which it's been accelerated. And we usually include a minus here because work is equal, or change in work done, is equal to change in potential energy for a charge. We're ignoring gravity and so on. We're just looking at electrostatics. Okay, and you'll recall that the electron has the fundamental charge, or the proton for that matter, has the fundamental charge, and we can represent that with a lowercase e. Now, what is E equal to? Well, it's a fundamental constant of the universe. It has an approximate value of 1.6021766, and you get a little ellipsis here, times 10 to the minus 19 coulombs. So that's your fundamental charge. Obviously the electron, you'd have minus E. For the proton, you'd have plus E, etc. But the point being, this is your fundamental charge unit, and this is work done by accelerating some charge through a potential difference. Okay, so this allows us to introduce our new unit. So the new unit is a unit of energy. So we could say new unit for energy, although as we'll see it's actually used more broadly than energy. The new unit is the electron volt, abbreviated EV. Alright, so what is this EV equal to? Well, 1 EV is approximately 1.602, and we could add on all the 176 ... times 10 to the minus 19 joules. So what is an electron volt? Well, it is the energy that you would get from accelerating an electron or a proton through a potential difference of 1 volt. Now obviously you could obtain this by noting that work being equal to Q delta V would simply be E delta V, and we can drop the minus sign here by just noting that if we're accelerating a proton or accelerating an electron, we're just kind of changing the direction that it moves through this 1 volt. So this is the work that is equivalent to 1 EV, and that is of course going to be the charge, 1.602 times 10 to the minus 19 coulombs times a volt. And so we could also say 1 joule is equal to 1 coulomb accelerated through 1 volt. Alright, so that's our new unit. That unit is essentially going to be very handy for measuring all sorts of things in terms of quantum scale items, objects. In other words, if we want to measure the energy of a photon, or for that matter an electron or a proton or an atom, or a transition within an atom, which usually corresponds to a photon, these usually are done in terms of EV, KEV, or MEV. And actually we now can introduce a sort of conceptual example, if you'd like, which is how many EV do things correspond to. And so there's kind of this energy equation that you get from Einstein, from his special relativity, and it then shows up elsewhere. And you've probably all seen it before. It's maybe one of the most famous equations in physics, in the sense that people outside of physics know it. That is that the energy, this is usually a rest energy, is equal to mass times c squared. E equals mc squared. Okay, so an electron at rest, has an energy from E equals mc squared. E is about 500 keV. Again, this is approximately 500 kilo electron volts, or if you'd prefer 0.511 mega electron volts. For a proton at rest, you get a few MEVs, hundreds of MEVs. It's about 938 MEVs for the proton. And then for the neutron, which is slightly bigger than the proton, the neutron at rest, E sub n naught, is about 939. And of course, in both of these cases, I've really rounded. Why am I retaining out to this first decimal point? Because that is the sort of like largest figure in the electron mass. So we'd have like 0.5 is the mass of the electron in terms of these numbers, as you can see. All right, so that is our new unit. What is it used for? Like I said, it's used for measuring energy, but it can also be used in combination with these other constants, in particular with the universal speed limit, to measure other things like mass or momentum. So our universal speed limit, which is also the speed of light of vacuum, universal speed limit, and we'll just call it speed of light. I'm shorthanding this from speed of light in vacuum to speed of light, is given by c. This one you should be familiar with, that c is equal to 2.9979245 times 10 to the 8 meters per second. So this is exact. This is a fundamental constant of the universe, and our entire metric system has been redefined in such a way that this is an exact number. Every digit after this 8, if you want more significant figures, is a 0. Now, that's not necessarily a new constant, but it's new in the sense that we can combine it with this Einstein equation that we just evoked to get masses of things. So mass can now be written in terms of E over c squared. Or in other words, we can put the units of mass as eV per c squared. So your electron mass is approximately 511 keV per c squared. And note that if I multiply both sides by a c squared, I end up with an energy, and that's 511 kiloelectron volts, etc. Momentum likewise can be written in terms of eV per c. What about angular momentum? Does it come out in units of eV.s? Well, yes. It could now be written in terms of eV seconds instead of joule seconds. But speaking of angular momentum, and this is where we introduce our other new constant, we have the Planck constant, or Planck's constant. And usually we use an h to represent the Planck's constant. Planck's constant has a value, h, of approximately 6.62607,004 times 10 to the negative 34 joule dot seconds. But we can also write that in terms of eV dot second. I'm not going to keep so many digits of precision here. You can get more if you want by doing the unit conversion. But this is about 4.136 times 10 to the minus 15 eV dot seconds. So what is Planck's constant? Well, it's basically what's called the quanta of action. Now it has units of angular momentum. It's highly useful for figuring out stuff like energy. It basically does things for you like converting between energy and frequency for a photon. It also, in the terms of a different constant, Planck's reduced constant, h bar, can get you energy in terms of angular frequency for a photon. And as we would find out using the de Broglie hypothesis for other things like electrons and protons and so on that also have associated wavelengths. So h bar, for what it's worth, is defined as h divided by 2 pi. I think we're all familiar with 2 pi already, so we're not going to belabor that particular point. So here's, for example, energy of a photon. E is equal to h times f, which is also equal to h bar times omega, which is also equal to hc over lambda. And that's all for today. Thanks for watching.